Okay, we've been talking about variation and measures of variation. So the first thing that we want to do today is a formula, and it's called coefficient of variation. It's relatively easy to use. It's just a formula. The abbreviation is CVAR, CVAR. And here's your formula. It's S. What does S stand for?
Standard variation.
Standard deviation of the sample. Okay, everybody remember that from 2 days ago? Divided by X bar. Everybody know what that is? The sample mean. Okay? And again, I'm giving you all these symbols. You guys have to start memorizing these symbols and know exactly what they stand for. Okay? And then you're going to multiply this by 100. And then you're going to write down your answer as a percentage. Okay? And again, this is called the coefficient of variation. Abbreviated CVAR, it's your sample standard deviation divided by your sample mean times 100, and you write your answer as a percentage. Okay? Let's jump right into an example. The average test score on a history exam was 70 with a standard deviation of 5. On a math test, the X bar was 85 and S was 4. Compare the variations. Okay? So we have a history exam. And they say on the history exam, the mean was 70, so X bar was 70. And the standard deviation was 5. Okay? That's pretty much all you need to get the coefficient of variation for the history exam. So go ahead and compute that one first. Go ahead and compute the coefficient of variation for the history exam. So just following this formula, you're going to have 5 divided by X bar, which is 70. Put that in your calculator, multiply that by 100, and see what you get. So 5 divided by 70 times 100 . 7.1429 if I go 4 decimal places. Everybody get that? 7.1429. And then we're going to write that as a percent. So 7.1429. And we write the answer with a percentage symbol. Coefficient of variation for the history test. Okay? I also said there was a math test. And on the math test, the mean was 85 and the standard deviation was 4. Okay? So utilizing that information, go ahead and compute the coefficient of variation for the math test. So again, very similar. We have S is 4 divided by X bar, which is 85. Put that in your calculator. Multiply it by 100. And then you're just going to drop a percentage symbol onto the answer. So 4 divided by 85 times 100. If I go 4 decimal places, 4.7059. That's my coefficient of variation for this particular math exam. Okay? Now, on a homework or quiz or something like that, the question will say which was more variable. All right? So whichever has the highest number is more variable. Okay? So that's the kind of the question that is asked. Which is more variable? So in this case, clearly, history would be more variable because it's a bigger number. All right? That's pretty much it for coefficient of variation. You're just following this formula. Okay? Any questions on that?
So on the test, you're not going to ask us what the coefficient of variation is. You're going to ask us what's more variable?
Yes. If it's on a test, that's how it would be phrased. Yes. And then you'll have to know, oh, just find the coefficient of variation. But obviously, I will have to give you the mean and the standard deviation. So hopefully that will clue you in a little bit. Okay? All right, great. Let's continue on. The next thing we want to talk about is called Chebyshev's theorem. So let me write it on the board. and then we can discuss it. Okay, Chebyshev's theorem. First of all, how you spell it? Chevy. Shebbs. Okay, Chebyshev's theorem. The proportion of values from a data set that will fall. The proportion of values from a data set. I'll put any data set. That will fall within k standard deviations of the mean, within k standard deviations of the mean, will be at least and finally, here's the formula. 1 minus 1 over k squared. Okay? So my formula is 1 minus 1 over k squared. Okay? And the lowest k can be is 1. So I'm going to put k has to be greater than or equal to 1. Okay, so as you're finishing writing this down, let's walk through it one more time. So the proportion of values. So the proportion or percentage of all the values from any data set that fall within a specific number. So k is going to be a number. Within, let's say k was 3. Within 3 standard deviations of the mean will be at least, and then you're going to put 3 here. 1 minus 1 over 3 squared. Okay? Let's do that example. Let's say, hey, example, let's let k be 3. Okay? So if k was 3, then we're using Chebyshev's theorem to say the percentage of all values in that data set that fall within 3 standard deviations of the mean will be at least 1 minus 1 over 3 squared. What is 3 squared? 1 minus 1/9. Okay, so in our calculators, 1 minus 1/9 is approximately, it's 88 and the 8 repeats, right? So we're looking at approximately 88.89%. That's how Chebyshev's theorem works, okay? So for any data set you give me, the percentage that will fall within at least 3 standard deviations of the mean will be at least 88.8%. Okay? All right, calculate the percentage for me for k equals 2. 2k equals 2. And tell me what you get. One minus 1 over 2 squared, which is 4. What is 1 minus 1/4? Yeah, it's 3/4, which is 75%. Okay? Within 2 standard deviations. So let's say we're looking at some data. This is saying at least 75% of all that data is going to fall within 2 standard deviations of the mean. That's what that means. Okay? Within 3 standard deviations, approximately 88.89% will fall within 3 standard deviations of the mean. Okay? All right, let's do a couple of examples where we use Chebyshev's theorem and see if we understand how it works. All right. The mean of a distribution is 20 and the standard deviation is 2. Okay, so the information given in this example is the mean of a distribution is 20, and the standard deviation is 2. That's given information. All right, question 1. Using Chebyshev's theorem, at least what percentage of values will fall between 10 and 30? So what percentage of values will fall between 10 and 30? What percentage of values will fall between 10 and 30? Okay, so first, what's the mean again? 20. So I have a 20 kind of as my mean, right? And I want to go all the way out to 10, and I want to go all the way out to 30. And I want to know roughly what percentage that's going to cover of the data, okay? What's the standard deviation of this thing? 2, right? So if I start at 20 and I add 1 standard deviation, where do I get to? 22, right? Is everybody with me? If I add another standard deviation, where do I get to? 24. How many standard deviations do I have to go out until I get to 30? 5. Is everybody with me on that? So if I add 1 standard deviation to 20, you get 22. If you add another, you get 24, 26, 28, and 30. So that's 5 standard deviations, okay? Let's make sure that matches over here. If I subtract 2 from 20, I get 18, then 16, then 14, then 12, then 10. So it's 5 standard deviations, okay? So that's telling you in Chebyshev's theorem that k is equal to 5, all right? So we need to know how many standard deviations away we are. It's 5, okay? So now I'm going to cue up Chebyshev's theorem. K is 5. And what does the theorem say? 1 minus what? 1 over 5 squared. So 1 minus 1 over 25. So we go to our calculators. 1 minus 1 divided by 25. And you get 0.96. Okay? So the answer to this question is at least 96% of the values fall between 10 and 30. Okay? So your answer is at least 96%. Any questions on doing that problem? Yes?
Why is it at least 96%?
That's what the theorem says. It's at least that. Because it could be, you could have a data set with a mean of 20, and all values could fall between 10 and 30. It could be 100%. But Chebyshev's theorem says at least this number. Okay? Questions on doing that one? Yes?
Would it be wrong on a test if you didn't put at least on it?
I would just probably write in at least and take off 5 points. No, but just, yeah. All right? Any other questions? Okay, let's try another example. Using this same setup, at least what percentage of values will fall between 12 and 28? Okay, so using the same setup, you guys do this one. What percentage, at least what percentage of values will fall between 12 and 28? Pretty much the same problem, but now we're doing 12 and 28. Okay, go ahead, take a minute or two and see if you can solve that one for me. So count how many standard deviations it takes to get to those ends. Use that as your k number. Plug it into Chebyshev's theorem and see what comes out. Yes?
Are you doing decimal places or like 96% or
Yeah, that one actually came out to exactly 96. So if it does have decimals, yeah, go out.
all the way out?
Yeah.
22.
Or
Our rule's 4, so go out 4. What are you guys getting for k on this one?
4.
4, right? So make sure you get k is 4. Get that right first, and then go to Chebyshev's. Okay? So 1 minus 1 divided by 16. 93.75, right?
93.75.
So 93.75%. And again, when you write down your answer, just write at least 93.75%. Okay. Any questions on Chebyshevs? This is roughly how it works. Figure out how many standard deviations it is, and then plug it into the theorem. Okay. Chebyshevs is for any distribution, any data sets. Okay. We have a distribution that's called normal, which is bell-shaped. So we have another theorem that we use for data that is in a normal distribution. Okay. It's called the normal or empirical rule. So just make sure in your notes, Chebyshev works for any distribution. The next rule I'm about to put on the board only works for normal distributions. Okay. So make sure you know the difference there.
So far have we only been working with normal?
No, we haven't done anything yet. We just did Chebyshev's, which works for anything. Okay. But now, yeah, let's do the normal rule. Okay, when a distribution is normal or bell-shaped, so this is the normal, also known as the empirical rule. When a distribution is normal, bell-shaped, this is our rule, okay? Approximately 68%, approximately 68% fall within one standard deviation of the mean, okay? So approximately 68% of the values fall within one standard deviation of the mean. Okay, and again, I'm abbreviating, but we all know what that means, right? 1s of x bar. Approximately 95% fall within two standard deviations of the mean. And nearly all, and I believe in our book it says 99.7%, fall within three standard deviations of the mean. Okay? So if you're dealing with a normal curve, a normal distribution, these are the percentages that we're going to go by. You don't have to do the k equals thing with Chebyshev's. You just know within one standard deviation, you're roughly covering 68% of the data. Within two standard deviations of the mean, you're covering roughly 95%. And within three standard deviations, you're covering roughly all of it, or 99.7%. Okay? And again, this only applies for a normal distribution. Okay, good. Let's do an example. If you have a normal distribution, bell-shaped distribution, it looks roughly like this. Okay? And a couple of things. In the very middle of a normal distribution, you have x bar, which is your mean. Okay? So your mean falls right in the middle. Now, if I go out one standard deviation on each side, so this will be x bar plus s, and this will be x bar minus s, then this right here covers roughly this area. That's roughly 68%. Okay, so I'm just going to do a big 68%. That's roughly 68%. Okay, kind of doing a visual presentation of what we just wrote on the board. If you go out another standard deviation, so now we're x bar plus 2 standard deviations, x bar minus 2 standard deviations, then this here is roughly 95%. Okay, from this endpoint to this endpoint. And then again, if you go out one more standard deviation, we're getting toward the end here. Then that's nearly all, or approximately 99.7%. Okay? So that's your visual interpretation of what's going on here. With a bell-shaped or normal curve, the mean's right in the middle, and you're branching out each side. Okay? Question?
So this is a shortcut.
I'm sorry?
So this is a shortcut, so then you don't have to do the formula.
Well, you have to do the formula if you don't know that the distribution is normal. Does that make sense? Because that works for any distribution. If you're given that the distribution is normal, then yes, use this. Okay? All right, so for example, I'm going to tell you, hey, scores on a test were normal. Okay? Let's do an example. Scores on a test were normal. And the mean was 70, and the standard distribution was 10. Okay? So again, I'm telling you that it's normal, so you're going to use the rule that we just put on the board. Question number 1. Approximately 68% of the scores fall within what two test scores? Okay, so you tell me. The mean is 70, and we're saying 68%, so how many standard deviations are we doing for the normal rule? 1. So if I go up 1 standard deviation and down 1 standard deviation, what scores is that? 68. So we're saying roughly 68% of the people that took the test score between 60 and 80. Does that make sense? Okay. Roughly 68% of the people that took the test scored in that range. Okay, let's take it up to 95%. 95% of the people that took that test scored between what two scores?
150? 50 and 100?
50 and
90.
90, right, just one more standard deviation. Okay? Does that make sense? So if you're looking at the range from 50 to 90, that's covering 95% of the people that took it. That's what the normal rule says, okay? If I go to 3, 99.7, or nearly all are going to fall within what two test scores?
40 and 100.
40 to 100. Okay, does that sort of make sense? That's what the normal rule says. And so you'll have questions in your homework that are pretty much like this, where you'll have to figure out the values that fall within a certain percentage. Okay? Is it possible that somebody scored a 38 on this test?
Yes.
Sure.
So
Where would that person lie?
0.3%.
Yeah, in that 0.3%, right, that we're missing. Okay? Is it possible that somebody scored a 0 on this test? It's possible, but it's highly unlikely. Why? How many standard deviations do I have to go from 70 to get to 0? 7. So we're at like 7 standard deviations away. So that's pretty unlikely. Okay? Okay, good. I want to kick in a little bit into the upcoming lecture, which is on measures of position. So since we're talking about this normal rule now, let's talk about one of our first measures of position. Okay? And that is our what's called Z-score or standard score. Z-score, also referred to sometimes as a standard score. So I'm going to define this just using statistic symbols, and I want you to tell me what it means. Okay? So your formula for finding a Z-score is as follows. X minus X bar over S. Okay? Now if you understand these symbols, then you'll know what the definition is. All right? So let's take that last example we just looked at, right? What was my mean for that last example? 70. We were doing test scores. The mean was 70. What was the standard deviation? 10. Okay. Let's say I wanted you to find the Z-score for the grade 85. Somebody made an 85 on that test, okay? Could you calculate the Z-score for the person that scored 85?
Yeah.
What would you do?
85.
85 minus 70 divided by 10. And what do you get?
Well, you said Z was 85?
No, we're trying to figure out.
Yeah, so X is 85, right?
Yes.
Okay.
X is the individual score.
Yeah.
What does this come out to?
15 divided by 10, 3?
15 divided by
No,
10,
my bad. 1.5. Yeah,
1.5.
which is 1.5. Okay, now let me see if I can blow your mind with what I'm about to say. The person who scored 85 scored exactly 1.5 standard deviations above the mean. Is that true? Is 85 exactly 1.5 standard deviations above the mean? Yes.
Yeah.
Okay. That's what your Z-score represents. It's how many standard deviations you are above or below the mean. Okay? And here's the formula for it. You just take your individual value, you subtract the mean, and you divide it by the standard deviation.
It's how many scores you are above or below the mean?
How many standard deviations you are, yes.
How many above or below?
Right.
That's what Z is.
Yes. Okay? So, there are three things that can happen, right? What can happen? Well, your Z could be positive. If Z is positive, what does that mean?
You're above.
You're above the mean. You scored above the mean, right? What else could happen? Z is negative, which means you're below the mean, right? In this example, you did a test score below 70, okay? What's the other thing that could happen? How would you get a 0 Z-score? Which means you scored what? 70. If you scored a 70 on this test, then you scored right at the mean, and your Z-score is 0, okay? So let's put all of this together. Let's say I had a Z of 2. That means I scored 2 standard deviations above the mean. So clearly I scored higher than 70, and in fact I scored what? 90, okay? If your Z-score is negative, say your Z-score was -1, you scored 1 standard deviation below the mean, so in this example you scored 60, okay? If your Z-score is 0, you scored exactly the mean, you scored exactly 70, okay? And that's how it works. Any questions on this? You have to be really, really good with Z-scores, okay? Because that's going to stay with us the rest of the semester. All right? Any questions on anything? Yes?
Will X always be provided, or will we have to like work backwards?
Yeah, so just keep in mind that X is an individual value from the sample, but sometimes they'll give you Z and X bar and S, and you'll have to find X.
Okay.
So that will come up, yes. Okay? Yes?
Yeah, you talked about how like the test scores or whatever were normal.
Yes.
What is that? Well, how do we
It
know
just
if it's
means
normal?
bell-shaped. So it's a, you know, when you guys are talking about a bell-shaped or a bell curve, it means the scores fit into that. Okay? And a lot of problems in statistics, they'll say, given this is normal or assume this is normal. So you can use all this.
What does a non-normal curve look like?
Could be anything.
All right.
Right? Like if I took the ages of people in this room, it's probably not normal.
Mhm.
Okay. Other questions? Okay, good.